Hello, today we're going to talk about photoelectron spectroscopy. So let's talk about ionization energy or binding energy. We need to talk about this first before we get into the process of photoelectron spectroscopy. So I'm going to use a Bohr model to illustrate this. And remember, Bohr models are not perfect, but it's useful in some cases. We have a nucleus, right? And then the first energy level electrons are closest to the nucleus. Second energy, they get a little bit further away, right? So there's a couple things going on here. When you have ionization energy, or binding energy as it's sometimes called, it's the energy required to remove an electron from the atom. Energy required to remove the electron. So when you remove an electron from an energy level that's really close to the nucleus, that's going to take a lot more energy than if you were to remove an electron from an energy level that's further away. And remember, that's because our nucleus has protons and neutrons, but protons are positive and the electrons are negative. So the closer it is to the nucleus, the greater the attraction between those opposite charges. So it takes more energy to remove an electron that is closer to the nucleus. Now, if we think about those orbitals we were talking about before, which are a little bit more accurate than the Bohr model, you have like a 1s is the lowest energy, and then 2s, and then 2p, and then 3s, etc. And this is the lowest energy level, and this is the highest energy level of the set. Like, you always start from the lowest, work your way up. But when we're talking about ionization energy, I'm going to use an IE, ionization energy, it's going to take the most energy to remove an electron from the 1s because it's the closest to the nucleus. It's being held on the tightest by those protons. So as you move further and further up, the ionization energy decreases. So now photoelectron spectroscopy basically plots that information of ionization energies on a graph. So what it does is you'll have binding energy or ionization energy on the x-axis. And on the y-axis, depending on the graph, sometimes they'll call it number of electrons, or sometimes they'll say it's like intensity or something like that. But I'm just going to use number of electrons to make it simple. Number of electrons. So whichever electron has the highest energy is the 1s. So let's say, for example, we have a 0 to 100 on our binding energy. So they use peaks to graph electron energy. Instead of just like a bar graph or a line graph or something like that, they use these little peaks. That's what they call them. They're like little triangles. So the one with the highest energy is going to be 1s. And how tall the peak is the number of electrons in that orbital. So the 1s, s can hold up to 2, right? So if I would have, say, 2s would come next. And then after 2s comes 2p. So if s can hold 2 electrons, p can hold up to 6. So this would have 6 in it. See how it's 3 times higher? Because it has 3 times as many electrons in it. So let's say then the next electron is here. So that would be 3s, but it doesn't go as high up as the 2s or the 1s. So that means it must only have 1 electron in it. So that means if you counted all of the electrons total, 1, 2, 3, 4, 10, 11, this would be 11 electrons. So it would be sodium's photoelectron spectroscopy graph, or photoelectron spectrum. Now, if I were to change that and go ahead and make it the full height to 3s, now that would be 3s2, and now that makes that magnesium instead with 12 electrons. Now the annoying part of this is that sometimes they will flip the axis on you. So sometimes they'll put the highest energy on the left and the lowest energy on the right, but it's not consistent. So you always have to read the axis. Highest energy is 1s, and then work your way out from there. So here's a better image of sodium's photoelectron spectra. So, and again, we're seeing the number of electrons on the y-axis. So you're seeing the binding energy on the x-axis there. But look at the values. See the 1000 and 0.1. So the axis is reversed. The highest energy one, the one furthest to the left in this case, this would be the 1s. Then you have 2s, then 2p, then 3s. And again, this goes up to 2, right? 2, 2, 6, 1, like that. So those are the 11 electrons in sodium. I highly encourage you when you're approaching questions like this, annotate your test question, write the orbital for each of those peaks. Occasionally they'll ask you to compare. So there's 2 graphs here. I know it looks like 4, but there's only 2 graphs here. It's just the scale is kind of wonky. So this goes from, for just looking at nitrogen, this goes from 0 to 10, and this goes from 10 to 100. So this is still the highest energy because it's close to 100. Its highest energy is always 1s. And then the next highest is down here. This would be the 2s. So this would be 2p. All right. And it's kind of annoying when they split the graphs up like this because it's harder to tell that they're the same height, but since they are the same height, those are the 1s2 and 2s2, and this would be 2p3. It's just a little bit taller. And then for oxygen, same idea, highest energy, this is 1s, and then the next highest energy, 2s and 2p, this is 2, and then 4, this is twice the height. Okay. So that's all the same. One thing that they could do, though, is they could ask you to compare them to each other. So look at the energy for a 1s electron in nitrogen is 39.6. For a 1s electron in oxygen, it's 52.6. So the way that you can explain that is using the protons. If you're looking at the same electron or same electrons, then the only other thing you need to look at is protons. So nitrogen has 7 protons and oxygen has 8 protons. And it's those extra protons that are causing the 1s to have a greater binding energy. There's more protons, there's more pull, more attraction. It takes more energy to remove.